Let's check out the overview of this applied fluid mechanics course. This is essentially part number 1, which is incompressible flow, and I'll explain you later why I choose to split this course in 2 parts. So let's check out what this video is about, the overview of the part number 1. We're going to see the difference between compressible flow, which is part number 2, and incompressible flow, which is part number 1, which is this course. Why is it important to study this incompressible flow? Who should take this course, or who is this course intended for? And especially what is this course and what is not. So what we're going to see and study and what we are not going to study. And let's check out how this course, essentially part number 1, incompressible flow, is structured. And finally we check some textbooks. So first things first, let's see why I choose to split part number 1 and part number 2. Essentially because part number 1 is incompressible flow, such as fluids with constant density, normally is liquids, and many gases with no change on temperature and pressure in its operation, which this is not very common. Normally you change either temperature, pressure, or even volume. So you know, with the ideal gas law, if you change any of these, you will have something that is not constant in density. The good thing is that this is pretty easy to model, so it's very easy to model it in the mathematical equation. Actually, we're going to use the mechanical energy equation, and this is mainly about liquids. So moving liquids, moving and pumping, the height of tanks and friction loss, etc. We're going to see that in a little bit. And part number 2 is essentially just compressible flow. And this is very interesting because we actually have to model density as a function of temperature, pressure, and volume. I mean, it says complex, but it's actually not that complex. But of course, if you compare it with incompressible flow, it is relatively complex. Now, examples, essentially moving gases, because moving gases, they have friction. When they get friction, they increase their temperature. If they increase their temperature, they have pressure losses. Due to friction, the temperature increase makes the gas to expand, and therefore you have always a density change with respect of temperature and pressure. So that's why I decided to split the course into part 1 and part 2. So probably if you just want to see the incompressible part, or the compressible flow study, you just need to check out part number 1. So what's this course essentially about? The incompressible flow is the art, I call it the art of moving fluids at constant density. So we're going to check out some theory behind this phenomena. You have to check out transport phenomena or momentum transport. You're going to see the application of those concepts in the applied theory or applied examples, real life problems in engineering, and so on. We're going to check out the type of equipments, and not only what type of equipments there exist, but also we're going to see or study how to design them and how to operate them correctly. So once you finish this, you will know about pumping, about fluid flow measurement, about friction loss, pressure loss, and so on. So the typical keywords you will be hearing or watching and studying is pumping, friction loss, the mechanical energy equation. Maybe you recall Bernoulli Equation or Torricelli's law. It's okay. We're going to check out this. We're going to study this. We're going to see a little bit on piping and friction loss, type of pipes, cylindrical pipes and non-cylindrical pipes, such as this maybe. We're going to see agitation and mixing, which is a very important concept not only in compressible flow but also in reactor engineering. You always need to have a perfect or very good agitation and mixing. So this is essentially what's this about. So let me show you a very typical problem that we will be studying is, for example, this operation. We have let's say we have here a plant that needs to have a reservoir here, and it has an intake. And we have a discharge. So we use water, let's say, to cool some processes right here, and we need to move these liquids to the discharge. So you can see there's a height here, so probably you know that with the help of gravity we have no problems. But we also have a power plant here. Maybe we need a pump because we need, let's say we have a very high pressure loss, so we need to compensate that in order to have it in the discharge, which will have a atmospheric pressure. Not only that, the velocity, we're going to see that many here, the velocity, they have different diameters. We're going to see later that different diameters means different speeds, because this is a continuous flow. And we're going to see, for example, how much pump energy we need, how much friction loss we're going to have, what is the pressure that we should have let's say here, in the suction of the pump, and so on. And this one is easy actually, because you have it here up. What happens if you actually have here the suction and you want to take it to this here? Well, we're going to see that as well. This is the very typical example how to move a liquid from part A to part B. And what else? I think it's essentially everything. Let's go to the next one. Oops. So why pumping? Probably you know this. It's a very typical example. We have this. This is Alaska, one of the most richest oil regions in the world. And they have many petroleum here, and they start pumping it. You know that by theory, if you want to move a liquid, here, you want to move a liquid, you need to add work. It won't move alone. It could probably move alone if this was, I don't know, maybe 10,000 feet in height, and it was all straightforward to here, this point, 0 feet. Yeah, maybe you could move it, but this is not reality. We actually have no difference on height, and we need to pressurize each point in each pump station. For example, pump station 5, 6, 7, actually we have 12 pump stations. So why is it important? Because we need to know the energy requirements to move that fluid. We need to know what type of unit operations are needed to do that. Do we need a valve? Do we need a pump? Do we need to measure flow? What's the friction loss of each fitting, each valve, each equipment? We need to know also how much are we losing due to friction, because we know friction is everywhere and we cannot avoid it, but we need to calculate it to know how much maybe money we are going to need, or how much pump is required to overcome that friction loss. And of course, once you have all this knowledge, you will know the limitations of a pumping system. Maybe if I tell you we have this tank here and we have this little pump, and we want to take this fluid to another place of greater height, well, you know that maybe there's a maximum speed, flow, or rate that we can't operate. So maybe we're working with 10 gallons per minute and you want to check out if 15 gallons per minute is possible, or economically speaking possible. So we're going to know the limitations. And once again, the type of equipment used in the industry, because one thing is what you use in the lab, so for example pumping systems in the lab, versus the pumping that is actually used in the industry, huge pumps, centrifugal pumps, and so on. We're also going to check a little bit on piping. What's a pipe? Why we use it? Why it's cylindrical? Some profile, velocity profile, this one versus viscous profiles, and so on. Many type of materials used, commonly in the industry, the steel. But there are many other applications such as plastic, PVC, and so on. We also check out some important concepts on measuring the flow rate, because actually if you go to a chemical plant, you will see only a tube. You will not see how much substance is moving, and even though you could actually see it, you will need to know the speed of the fluid. So it's kind of difficult to measure it, but we will see how we can measure that. And of course, pressure drops. Pressure drops means that essentially you're going to lose pressure, and pressure is essentially force per unit area. So force, you also need work to do that force, moving the fluid. So if we have pressure drop, we need more energy. And finally, we check out some things on agitation versus mixing, and maybe if you're not an engineer or you don't know this difference, it's actually pretty important to know the difference, agitation versus mixing. And finally, the correct equipment design. I mean, when you're doing the numbers, how much, if you have one task to do, you have fluid in A and you want to move it to fluid or point B, you want to design it. And once it's designed, for example, you already have a pump, how can you move, change piping and so on to operate that? Is it better to operate the pump at 3,500 revolutions per minute, or is it better to check and change the impeller size? And what's the better or the best operation point? So hopefully you're getting the idea of what we're going to check and do and study in this course. But if you, I probably recommend this course for students or even engineers that want strong fundamentals on fluid mechanics. Essentially, fluid mechanics as theory and as applied theory, I think is very recommended. We're going to check out the theoretical concepts, but what this course is about is mainly the application of those theoretical concepts. How to solve real-life problems. We're not going to see crazy theory. We're going to see the most basic theory in order to solve real-life problems. Once again, equipment operation and design related to moving fluids. So one thing is knowing let's say, equipment, and other thing is design it and operate it. We're going to check a little bit on instrumentation, measurement, fluid rate or rate of fluid flow, and piping. So I will definitely recommend for engineers, especially the ones that need to calculate fluid flow of engineers and need to calculate the pump flow of a very viscous oil or a very light oil or even gas flow in a petrochemical plant. Mechanical engineers, well, because you are going to use pumps and you need to know the change in pressure, the delta P, the pressure needed in suction. Chemical engineers, well, of course, if you are in a chemical plant, you will need it because we need pumps to move fluids, and we have many liquids or substances that are in liquid form, so we can use that. Electrical engineers mainly to know why do we need or understand the basics on why do you have a very high load on the pump or why do you have a very low head on the pump. Process engineers, well, actually process engineer, whatever process you do, you're probably going to use pumps or move fluids. Civil engineers, in order to have the basics on housing and industries and so on, how to calculate the friction loss, how thick should you use the piping systems, how thin, how long, which material, and should you use pumping systems here or in the second floor and so on. And maybe also even industrial engineers. In order to calculate the amount of energy, is it possible to reduce money, to decrease the friction loss, or to change the operation of point A or the operation of point B? Nice. So what is this course about? It's about fluid mechanics, but don't see it the way of theory. See it more on the application. We're going to see in this part number 1, incompressible flow. We're going to check out some equipment, as I told you before, the design, the operation. I mean, this is literally numbers, and theory, of course. How do you choose a pipe or the suction pipe? What pressure should you have before a pump suction? Or if you have a series of pumps or parallel arrangement, what's better for you? We're going to study that. Once again, we're going to see a little bit on science, just the basic. We're not going to study that much on the science behind that. Of course, we need to see it, because if you don't study that, then you will have no idea of what we're doing. But I'm going to avoid to go to very theoretical concepts or abstract stuff. And of course, the thing here is we are engineers, so we want to solve real-life problems. So if you're in engineering, you're probably going to enjoy this course. So what's this course not about is essentially very heavy abstract theory of fluid mechanics. For example, viscosity theory, why is it more viscous, the shear stress. If we have this magical plate moving here to the right, all that stuff that you've probably seen in momentum transport or transport phenomena, we're not going to see that. We're not going to see that much into friction theory. We're going just to see the basics, how to calculate it, why does that exist. But we're not going to calculate, for example, calculate the friction of this little drop falling in the wall of the cylinder, or maybe even the flow if you have fluid and then crash in the ball. What's the friction? No, we're not going to see that. We're not going to study buoyancy, density, you should already know it, and the difference between weight and so on. This is, I mean, I'm going to suppose you already have some idea. So if you have at least the basic idea, it's okay. Now we go to momentum transport phenomena. As I told you before, this is actually co-wet flow. We're not going to see that. If you know it, it's very good you know it. If you don't know it, it's okay, you don't need it. Non-circular flows, for example, very crazy ones. I mean, we're going to see some, but just the basics. But for example, this flow calculate the, I don't know, the shear stress in this wall, or maybe we have this pipe and they tell you calculate the stress on this point right here. We're not going to see that. Very complex Bernoulli examples, because I could literally show you many crazy examples on Bernoulli, but actually if that does not happen in real life, why would you want to do it? I mean, yes, you can model very crazy stuff, but if you don't apply it in the real life, well, I don't see the point that much, at least not in engineering. And Navier-Stokes equations, all those crazy equations that talk about fluids and laminar flow. We're going to check out laminar flow, but essentially what we operate in the industry is turbulent flow, because we want high speeds. And once again, velocity profiling. We're not going to check out the profile. I mean, like for example, how long is this length, or is it plug flow, or so on. We're going to see a little bit on that, but we're not going to model that. We're going to see the theory and some, for example, examples, but we're not going to do numbers on that. And the typical boundary conditions, which is very common in transport phenomena, they tell you you have the radius and you have this shear stress, and the viscosity is actually 0, velocity is equal to 0, and so on. We're not going to see that. Also, dimensional analysis, such as the Buckingham P theorem or pi theorem. No, actually we just use this for Reynolds number and relative roughness. And you don't actually need to know where does these numbers come from. You just need to know how to calculate them. Flow around objects, cylinders, sphere, cubes, and so on. For example, this stuff. Well, we're going to see an example, but we're not going to use numbers, and I'm not going to ask you what's the temperature right here or what's the number right here. And I'm going to suppose that you already know a little bit on hydrodynamics, which is hydrostatic pressure and forces acting on this, which is very common in high school, middle school, and even physics courses in bachelor degrees. So what you need it essentially to move fluids. If you task, I know it sounds kind of stupid moving fluids, but actually there are many people working on this. If you need, for example, to move a fluid from point A to point B, how do you do it? What's the best way? Should you use a pump here or a pump right here? Should you elevate this point? Can you depress this point? If we use this material, we have this friction loss cost, but it's very cheap, so it's good for the investment or so on. We will also need to calculate the pressure drops in order to calculate the size of the pump. We also need to measure flow rates, because we cannot be producing without knowing how much stuff is going in and going out. Shall we increase the pressure? For example, many times you need to operate, you have a pressure at 1 atmosphere, and many times you want to send this fluid to a distillation column which operates at 3 atmospheres. Well, the distillation engineer tells you, I need this fluid at 3 atmospheres. Well, even though you don't know why, you need to do it. 1 atmosphere to 3 atmospheres. Will definitely help you in plant design. we're going to use as well the mechanical energy equations. So how much is generated and consumed and so on. And most importantly, many times you go to a chemical plant or anything that has a pump or pumping system, and it's already done, so you cannot move. The piping system is done, the point A and point B is already set, you cannot move it. The pump is there, you cannot change anything but valves and operation of the pump, like the size of the impeller and so on. So given that, how can you actually play with that in order to get the best economic or technical operations conditions? So what I'm going to ask you to know is essentially, you've been tracking my courses. I have a course on mass balance. Essentially, we're going to use just the basic balancing inlet outlet. We will have no reactions. We're going to have, of course, only moving fluids. Energy balance, just the basics, especially the mechanical part. I'm going to do a course on energy balance, but this is more on the heat requirements. Actually, this is the good course because we use the mechanical part, because you know energy is either heat or mechanical energy, and energy balance we check out heat, and in this course we check out work. Just the basics on thermodynamics, essentially, why do we need to heat material, how to model ideal gas laws, how to model real gases, and so on. A little bit on transport phenomena, especially the momentum part, just the basics, what's viscosity, flow in pipes, friction factor, wet flow, turbulence. Even though you might know it, we're going to review that as well, so don't worry if you don't know exactly what's the difference between kinematic, viscosity, dynamic, and so on. And fluid dynamics, just basic knowledge. Actually, just to know that pressure, how do you measure pressure in a pipe and so on. It's okay, we're going to see all through, so don't worry. For mathematics, actually you just need to know the basic arithmetics. Please be sure to know the geometry, because when I tell the student you just need to know the area and perimeter and volume of, I don't know, maybe the circle, a sphere, a cylinder, and so on, and they tell me, yeah, it's pretty easy, and then you get into the numbers, you ask them what's the perimeter of this cylinder, and you ask them what's the area of this transversional pipe, and they don't know how to do it. So please be sure, even though we're going to check this out, but just be sure to know it. Conversion of units is very critical in this course, not only from SI system, but English system to international system. For example, Fahrenheit to Celsius, pound force to pascals or newtons, and so on. Well, of course, decimals and scientific notation, and how to use fractions. But actually, if you ask me what's more important here, is the geometry. Have a good basis in math, which I probably know you have because you're studying engineering or something related to this, and please be sure to use the English system and know a little bit on the English system. If you are a English system native user, well, then you will have a little bit problem when you change to international system. And my recommendation essentially is for the SI system users, which is essentially 90% of the world, is just to know the conversions. Just check out what the conversion and go back to international system. Use the most logical system here, which is very easy to use, and forget on all the complex English system conversions. What you need to know in chemistry and physics is just, for example, pressure versus force. Please know the difference. How to change absolute to normal temperature, for example, Fahrenheit to Rankine, Celsius to Kelvin, Celsius to Fahrenheit, Fahrenheit to Celsius, and so on. Please know what's the difference between mass and weight, what's a mole, mass, weight, molar mass, mass fraction, all this stuff that for chemical engineers is actually very common. Maybe you're let's say, an electrical engineer, you have no idea. Well, please check out, this is literally basic chemistry. Check out your high school notes, or even, I'm pretty sure in YouTube there are many videos on how to calculate moles from a molar mass. And basic hydrodynamics and hydrostatics. Just know that the column exerted by a fluid, this is the height, and you know there's a density and gravity. Well, you know how to calculate the pressure exerted by that fluid. Once again, viscosity, but we're going to check it. Don't worry. The Bernoulli equation, I'm pretty sure you have heard or even used it. So if you have used it before, you're going to have an advantage. Friction factor basics. If you have no idea what's this about, no worries. We're going to check this out very deeply. And how to calculate the efficiency in work. For example, the efficiency for a pump is different for a efficiency in a turbine system. Good, now let's check out the books. I will be using essentially these two books for theory and exercises and examples. And this is mainly for fittings, pipes, and valves. Friction, essentially for the friction part. Let's check out. I'm pretty sure this is the 7th edition, actually. Where is it? Well, yeah, 7th edition. But I think there's already the 8th edition. You can use whatever you have or want. It's unit operation of chemical engineering. Essentially, unit operations, you know, it's like pumps, compression, piping, flow measurement, and so on. It's written by McCabe, Smith, and Harrell. This is a pretty good book for chemical engineers and even for, I will say, essentially for engineers. We're going to check out many chapters on this book. I'm going to show you which chapters we're going to see, study, problems, and so on. Now, as the name implies, I actually love this book because this is essentially 100% our course. It's Applied Fluid Dynamics by Robert L. Mott, 6th edition. It's pretty good, essentially for any fluid mechanics because you have many theory behind that. And we have a lot of application of that theory. We're going to check out that. I would definitely recommend for any engineering field related to fluid mechanics. And once again, this is the flow of fluid through valves, fittings, and pipe. This is essentially just for the friction data. There's not that much theory, but actually it's very good for a reference book. So let's check course structure. Remember, this is Applied Fluid Dynamics course. And we have it in two parts. Part number 1, which is Incompressible Flow, and part number 2 is Compressible Flow, 60 and 40% each. So for instance, this is part number 1 and this is part number 2. If you check out, this is about 40%, and if you check out this part right here is 60%. Okay, this is part number 2. You are interested in gas flow and gas flow through nozzles, tubes, pipings, and compression, and also operations such as packed bed and fluidized beds. Please check out part number 2. Part number 1 will be essentially just this little block, the mechanical energy equations. We're going to see these a little bit more on the next slide, so let me show you just this. Piping, fittings, and valves is just theory. Energy loss due to friction 5%, flow measurement 5%, pumps 15%. Actually, this is very huge amount of material, and this is one of the core blocks. Then we go to incompressible flow application. Once you know all these, you know the mechanical energy equation, how to calculate friction losses, the type of pipes, fittings, and valves that there exist, and flow measurement equipment, and you know finally how to choose a pump. We're going to check out incompressible flow application. So many real-life problems and how to solve them here. And at the end, we check out a little bit on agitation and mixing. So let's see a little bit more content on part number 1, incompressible flow. But before actually checking out each block, I just want to tell you that you will always find an introduction to the block. So you don't waste your time, you just check out, and if you think it's very useful to you, check it out. You will check or see what's the best part for you and go on. So you don't need to actually study all the block. You just go here, see or check out what's useful for you and go direct to there. Now the theory behind, we're going to see the theory and then we're going to apply the theory for real life problems. We're going to have also explain problems, I mean with numbers and using the equations and so on. Solved problems are included in the web page, so check it out. We're going to have also a quiz section, which is essentially just theory. Pop quiz, for example, a 50 questions on pumps, how to use a pump, what's a pump, what's a pressure, suction, cavitation, etc. And of course, each block has its own conclusion. So when you finish the block, you don't get the idea that you're just like full of ideas. We're going to have the idea of this is to have, for example, what's this useful for, which block is going to need these blocks, which other blocks are needed or were needed for this, what we a review of all everything and so on. So let me show you AFT block number 1, the mechanic energy equations. So as I told you before, section 0 is a review, density, viscosity, friction, blah blah. Very important topic, gravitation constant, which in SI system is number 1, beautiful number 1, and for English system is 32. As usual, very strange. Why do we need the mechanical energy equations? For example, systems, how I apply systems. Why do we need kinetic and potential energy? You know, kinetic is about velocity. Something that moves definitely has energy. Something that has a very relative position with respect to gravity has also energy. The pressure head, famous pressure head, which is force per unit area, and inlet outlet work, how to calculate or account for pumping, compression, turbines, and so on. And we check out a little bit let's say an overview on friction loss. It's a dependent on trajectory and the nature of friction loss. Why do we have friction? And finally, we check out some examples. We do the Bernoulli's law example, Torricelli's law example, and the complete or full mechanical energy equation examples. So after that, it will be interesting to check out piping, fittings, and valves. We have the 3 sections. Essentially, section number 1 is pipes and types of material. What's a pipe? What type of material do we use? Roughness of the material, and sizings, which is very common in the industry. Then we go to fittings and flow measurement, actually stuff that you add or plug into your pipe in order to have a function. For example, you want a valve to control volume, you want a pressure meter to calculate pressure differential, you want a, I don't know, an elbow to change the direction in 90 degrees, and so on. The function of each and many common fittings used in engineering. And finally, as I told you before, valves. Common type of valves and why do we have many types of valves. Then we go to AFT block number 3, energy loss due to friction. So we have a little review of flowing pipes, the Reynolds number, laminar flow, turbulent flow. Then we check out section number 2, which is friction loss in pipes, because we also have friction loss in fittings and valves. Of course, you know that if you have a valve partially closed, let's say 90% closed, you're going to have a lot of friction there. So we see a little bit on Moody's and Fanning frictions or definitions of friction factor, the difference and which one we will be using. The Moody's famous diagram to calculate friction or relate friction, factor friction versus Reynolds number. And many equations, because actually it's pretty good to have equations so you can use them on Excels or spreadsheets or even calculators instead of having a diagram. Now, once we understand friction loss in pipes or pipe wall, we're going to check out what's the friction loss in that fitting or valve. For example, how do we calculate that? How do we do equivalences? Actually, if you were to have this elbow, what's the equivalent on a pipe. For example, having this elbow will be the equivalent of losing 2 meters of this pipe, and so on. Many types and many values of fittings and valves. So I told you before about measurement equipment, so we're going to check this in this AFT block number 4, section number 1, venturi tube. We're going to check out the introduction and how to do a mechanical energy equation balance, and why is it good to have a venturi tube and why is it bad, or disadvantages. Then we go and check out the orifice plate, which is easy to move and change. This is actually difficult to be changing every time. Orifice plates is good, but it's kind of expensive. And finally, some state-of-the-art measurement equipment such as thermal, mass flow meter, paddle wheel, magnetic, and many other devices. So then we check out pumps, AFT block number 5. This is essentially 5 sections. Section number 1 is theory. What type of pump do we have? Positive displacement, kinetic, and a little bit on pump performance, such as cavitation and so on. Then we check out the system curve. What's the system requirement actually? So if you have A needs to go to B, and you calculate the amount of energy required for this system. So this is the system head, and then we will do a system curve. We'll see that later. Then for different pumps, we're going to study, you make an energy balance here and an energy balance here, only on the pump. That will be the pump head, and we will do a pump curve. Not only that, we're going to see the impeller effect, the efficiencies curves, the pump power curve, the net positive displacement needed, and the velocity of the revolution per minute of the pump. So we will see a lot of pump curve here. And then finally we can go and see what's the best pump to choose. How to choose a pump, supplier data commonly added, and affinity loss, because many times we're going to have a diagram which is not complete, but with these rules, or these laws, we will be able to calculate a point away not included in our diagram. So for example here. Then pumping systems, pumping series, parallel pumps, and software or common software used to model pipes and pumping systems. We are almost done, guys. Once you know all the theory behind and how to calculate work, friction loss, pressure loss, and so on, we're going to check out applications, real life problems. For example, series flow. You have series flow is very common. For example, here you have, I don't know, maybe valve here, an elbow here, and you have this is, for example, 3 inches pipe, and this is a 2 inches pipe, and if you have, I don't know, maybe you have a pump and so on. How to calculate the head of the system, how to calculate the best pipe size diameter for this system, and even how to calculate the volumetric flow rate that best suits this problem. And finally, some pump selections. That was for series flow. For parallel and branch flow is a very other approach. For example, this is pretty common in the industry. You have here, it goes out and then meets once again in another place. This is parallel flow. Branch flow is a very interesting concept. It's actually more difficult and complex to model. For example, you have this point right here, and then this one goes right here, and this branches once again. And the thing here is that the flow meet again here in parallel flow, let's say with 2 pipes, and in parallel or branch flow with more than 2 pipes, for example, they never meet, so it's very difficult to calculate this. You will need to use software. And finally, but not least, we check a little bit on agitation and mixing, the difference, overview of equipment. Then we start to actually design the equipment, for example, power number and power requirement. Then we go and check out this very fancy stuff, which is static mixers and some software to model that. We're not going to see how to model it, just the software that exists to model that operation. And thanks God we're done. This was the end of the introduction of part number 1, which is Incompressible Flow. By now you should know the importance of this course, the course structure and content, that this is a course of theory but mainly application, and of course hopefully you know by now that part number 1 is Incompressible Flow, liquids. And I will definitely recommend you guys to start with part number 1. You can of course go directly to part number 2, but you study part number 1, you will get more easy part number 2. And I will definitely recommend you guys, if you're done with part number 1, go directly and study part number 2 once that you are fresh, that you can get it everything, because if you let time pass, then you will not remember part number 1, and part number 2 will be a little bit more tricky for you. And of course guys, I have a lot of problems for you. This is exercises and solve problems. Go and check out, go to chemicalengineeringguide.com, courses, choose applied fluid dynamics, go to part number 1, which is Incompressible Flow, and you will get a lot of solved problems, quizzes, these slideshows, and much more stuff. So remember guys that I will give you all the theory you want, but you need to practice by your own and repeat and repeat and fail and succeed in order to get mastery. So I will definitely recommend you go and check out all the problems and exercises that I have prepared for you on the website. Just go to the course and momentum transfer operation section or applied fluid dynamics, and you will see part number 1 here. And check out the quiz. And we're done. Whatever doubt, comment, inquire, whatever thing you think you might have, please send me an email or even tweet me. Like my Facebook page, in which I add many memes and videos and all related to engineering, process engineering, chemical engineering, and so on. And you can always check out the courses. That was everything guys. I think you're set. If you like the course, please go and check out the introduction of mechanic energy. This is AFT block number 1. And thank you for joining the course guys. See you in the next video.